only this pulse is produced in the string. Here total wave is moving along this direction and the wave is moving along this direction. Then the pulses moving perpendicular to the propagation of this wave direction. This is called a transverse wave. When a pulse is moving, then this pulse is moving along this direction and then this pulse is perpendicularly moving along the direction of the wave. This is called a transverse wave. And coming to longitudinal waves. Here longitudinal waves, for the longitudinal waves I am taking a vessel and this vessel is filled with air. This vessel is filled with air and fixed with the piston. Is fixed with the piston. Now here I am pressing this piston. Here I am pressing with this piston down and also again releasing the piston in the upward direction. When we press this piston, then the particles of this medium, the particles in this medium moves in the same direction as the piston is moving. And if we release this piston, that is if the piston is moving in the upward direction, the particles of this piston moving along the direction of the piston. That means here along the same direction the particles are moving. This is called longitudinal waves. Or if we take a string, here I am taking a support for this. I am taking a spring. This spring is attached to the support and if we drag this spring along this direction, if we just pull this spring along this direction, then in that spring this longitudinal waves produces and these longitudinal waves traveling along the direction of the wave propagation. Then this is the explanation for this transverse waves and longitudinal waves. Here next the displacement relation. Here displacement relation for the transverse longitudinal waves. Displacement relation. Here for this displacement relation we are taking I am taking a equation, that is y x comma t, y of x comma t is equal to a sin kx minus omega t. Here y of x comma t is equal to a sin kx minus omega t I am taking. Here in this y x comma t is the direction of the particles of the medium, and this a is amplitude and this k is the wave number and omega is the angular frequency and this t is the time. Now here this wave traveling in the medium, again it is the periodic. The wave, that is longitudinal waves or transverse waves, are the periodic waves. That's why this displacement relation, again I am taking y of x comma t is equal to a sin kx minus omega t plus phi. Here this pi is called a phase of the wave. Phase of the wave. Here this periodic function we can write again y of x comma t is equal to a sin kx minus omega t, that is a sin kx minus omega t plus b cos kx plus omega t we can write. That means here this is the periodic function of the wave pattern. Then by this we can write this theta, that is phi is equal to tan inverse of b by a. This theta, this phi is equal to tan inverse of b by a, and amplitude a is equal to square root of a square plus b square we can write. Here this displacement y of x comma t is equal to a sin kx minus omega t. This is the displacement relation. This we can write a sin kx minus omega t plus phi. Here phi is the phase, omega is the wave number or angular frequency, and t is the time, k is the wave number, then a is the amplitude. This is the periodic function. Then we can write a sin kx minus omega t plus b cos kx plus omega t. Then phi is equal to tan inverse of b by a, and amplitude a is equal to square root of a square plus b square. Here in this relation, if we take y of x comma t, a sin kx minus omega t plus phi. Here this is the displacement relation, that is along the positive x direction. The wave is moving along positive x direction. If this wave is moving along the negative x direction, then the displacement relation y of x comma t is equal to a sin kx plus omega t plus phi. This is along the negative direction, negative of the x direction. This is the relation for displacement y of x comma t, a sin kx plus omega t plus phi along the negative x direction. This is the displacement relation. Now amplitude. Amplitude. Here amplitude means the maximum displacement from the mean position. If the particles are traveling along with the wave, then the maximum displacement from the mean position is called amplitude. Here for example, here I am taking the wave. If this is the wave traveling in a medium, that is along the positive x direction, then here if we take this is the mean position, and this is called amplitude. The maximum displacement from the mean position is called amplitude. Here in this y of x comma t is equal to a sin kx minus omega t plus phi. Here in this a is amplitude. This a is amplitude. Already we know the minimum and maximum values for this sign is the sign value. This sign value is changing from -1 to +1. Here the sign value is changing from -1 to +1. That's why the amplitude A, this amplitude A is also changing from -a to +a. That means here amplitude is never be negative, that means the magnitude of this amplitude is always +a. This is the magnitude, but based on the direction, this value is changing, that is -a to +a. Here this a is the amplitude, that is magnitude of amplitude, but because of this sign values it is changing from -1 to +1, then this amplitude is changing from -a to +a. Here this phi is called a phase. Now phase, what is phase? Phase is nothing but simply it describes the displacement. It describes the displacement or velocity of the wave at a particular instant, at any instant of time. Here phase means this phase describes the displacement or velocity of a wave at a particular instant of time. This phi is called a phase. Here y of x comma t is equal to a sin kx minus omega t plus phi. In this phi is called a phase, and if for example this phi is equal to 0, if we take this phi is equal to 0, then it is called a initial phase angle. If we take this phi is equal to 0, that is called a initial phase angle. Now wavelength. Here wavelength is nothing but, here for example if we take this this is the wave, and for this wave here the maximum displacement above the mean position is called a crest, and the maximum displacement below the mean position, this is called a trough. Here when a wave is traveling in the medium, always the crest and troughs are forming. Here the maximum displacement from the mean position is called a crest, and the maximum displacement below the mean position is called trough. When a wave is traveling, always the crest and troughs are forming. Here now wavelength. Here wavelength is nothing but the distance between the two successive crests, or the distance between the two successive troughs is called a wavelength. Or wavelength means the distance between the displacement of the wave with a same phase difference or same phase. Here for example if we take this is one crest and this is one crest, then the distance between this crest to this crest is called a wavelength. This crest to this crest is called wavelength. Already we know this displacement relation is a periodic wave function. Then this periodic wave function, for example y of x comma t is equal to a sin kx minus omega t plus phi. Here for example at phi is equal to 0 I am taking, then y of x comma t is equal to a sin kx minus omega t. Initially the wave is at this place, then I am taking this wave is again repeating. Here for example at t is equal to 0, y of x comma 0 is equal to a sin kx. This a sin kx I am writing as a sin, that is sin kx is equal to, we can write sin k into x plus 2n pi by, okay, for every 2 pi phase difference, then this wave is at the same phase difference. Here the wave is at this position, then after 2 pi phase difference, the wave again at the same position, again it moves along the same direction. That is here we can write kx plus 2n pi into x, 2n pi into 2n pi. This we can write sin k as common, then x plus 2n pi by k we can write. Here after every this 2n pi phase difference, again this wave at the same position, at the same phase angle.